In this last set of lectures, we're going to talk about properties of Darboux or Riemann integrals, because now we know that both represent the same thing. And we're going to prove the following theorem first. So number one, every monotone function f on AB is integrable. Proof. So the only thing that we need to check in this case, remember that we have two criteria of integration. So if we can check one or another, then if that criterion works, then we're done. Let's suppose now if we have a monotone function, it's either monotone increasing or monotone decreasing. So let's suppose that it's monotone increasing. So suppose that f is monotone increasing on AB. And by the way, going for a moment to the statement of a theorem, when we say the function is integrable, we have to specify where. So it's, in this case, integrable, of course, on AB. All right, so let's say f is monotone increasing on AB. Let's fix an epsilon greater than 0. And what we want to do, we want to find a partition. Let's say if I want to test the first criterion of integrability, I want to find a partition P of AB such that U of Fp, the upper Darboux sum, minus L of Fp, lower Darboux sum for that partition P is less than epsilon. All right, so let's compute actually what we have here. So what is U of Fp minus L of Fp? We already encountered this object in the previous lecture. So U of Fp is a sum I from 1 to n suprema m of f ti minus 1 ti times ti minus 1. That's U of Fp, and L of Fp is essentially the same, except for the fact that you're using lowercase m's instead of capital M. Right, so infima instead of suprema. Then I can combine two sums, and the terms that I'm going to combine will have a common factor, right? This guy and that guy have a common factor of ti minus 1. So this whole thing then becomes the sum I from 1 to n And then we have capital M minus lowercase m and the whole thing is multiplied by ti minus 1. All right, so really I have not done anything dramatic here. I just wrote down the definition of the upper and lower Darboux, definitions of upper and lower Darboux sums, and I simply manipulated these definitions to combine the two expressions together. Okay, but now let's see. We have a function f, which is monotone increasing on AB. What does that mean? If the function is monotone increasing and I'm looking on any subinterval of the interval AB, then on that subinterval f should also be increasing, right? So f is, let me write this down, is increasing on AB, and therefore f is increasing on ti minus 1 ti for every I. And because of that, now I remember that capital M is a supremum of f on a subinterval ti minus 1, right, is capital M here. And the lowercase m is the infimum in that interval. And if my function is increasing, then clearly the supremum is going to be a maximum at the right endpoint, and or supremum actually is going to be a value at the right endpoint, and infimum is going to be the value at the left endpoint. So what we have is that capital M is going to be equal to f of ti, and the lowercase m is equal to f of ti minus 1, again, for every I. Okay, so then from this, and from this computation here, which I'm going to label as star, we're going to have that u of fp minus L of fp, that this is equal to sum from 1 to n of what now? Capital M is f of ti, lowercase m is f of ti minus 1, and the whole thing is multiplied by ti minus 1. All right. Okay, so then can I estimate how big this can be? Well, f of ti minus 1 I'm not going to touch now, but let's look at ti minus 1. So those are lengths of intervals from my partition. And last time we introduced the quantity mesh of the partition, which was equal to the maximum of the length of this interval, maximum of the length of these subintervals. Now, f of ti minus 1, the function is increasing. This is a positive number. This is a positive number. So if I replace these multipliers by their largest value, I'm going to increase the entire expression. And so this then is less or equal than the same sum, but I have to replace, I can replace f of ti minus 1 by mesh of p, right? That will make the whole expression bigger. So where the mesh of p? Well, actually, let me do one more computation here, and then I'm going to write the definition of mesh of p again. So now, mesh of p is a constant. So I can pull it out outside of my summation. So this is equal to mesh of p times the sum. And now, what exactly is this sum? Can I say anything about it? Let's expand it. So I have mesh of p times, on the first interval I have f of t1 minus f of t0. On the second interval I have f of t2 minus f of t1. On the next to the last interval I'll have f of t n minus 1 minus f of t n minus 2, and on the last interval f of t n minus f of t n minus 1. And then this is our old friend, that's a telescopic sum, right? Because f of t1 comes in with a plus sign and the minus sign, it will go away. F of t2 comes in with a plus sign and minus sign in the next expression that I'm skipping. And this is going to continue forever. F of tn minus 2 will cancel. The last term that will cancel is f of tn minus 1. Again, it comes with a plus sign and a minus sign. And so the whole thing then is going to compress to mesh of p times f of tn minus f of t0. And then remember that tn was the last point on the interval, which is b. T0 was the first point on the interval, so that is a. So what you got is mesh of p times f of b minus f of a. So again, this is because mesh of p was the maximum in I of ti minus 1. All right, so now what do I want? I want u of fp minus L of fp to be less than epsilon, right? So now, because of this bound that I found, what I want is to make this quantity less than epsilon. F of b minus f of a is a fixed number for my function. And how do I choose my partition then? I would need to choose a partition where mesh of p is so small that this quantity is less than epsilon. So now let's choose any partition P such that mesh of P is less than f of b, is less than epsilon divided by f of b minus f of a. What have I got then? I got that u of fp minus L of fp which I already determined is less or equal than mesh of p times f of b minus f of a. That this is going to be now less than epsilon over f of b minus f of a times f of b minus f of a, and f of b minus f of a is going to cancel, and so I just got epsilon. Right, and so the conclusion is, therefore, f is integrable on AB by the first criterion of integrability. And so we're done here.